Hi, good morning, everyone. This is the title of my presentation, Programmable Materials for Sensors, Actuators, and Manipulators for Soft Robotic Applications. This is a brief outline of this presentation. First, we will give the background about soft robotics, and then we go to the objective of this project and works. And we go to the major research and discussion. That is in the area of sensor, actuators, and manipulators. And we conclude with some future direction. So first, what is a soft robot? The concept of soft robot is to develop the functional part of robot using soft and stretchable material. Here we compare a simple gripping application using a hard robot and a soft gripper. As you can see with the hard robot, it's a very complex system. It involves numerous links, motor, and sophisticated sensor and a computational system to make sure that the force applied on this egg is correct amount. But if you want to perform the same functionality using a soft gripper, it's much more simple, both in fabrication and in operation. You don't even need a pressure sensor to perform the same task. So in that sense, we can say a soft robot can simplify some of the existing robotic technology. Now, in future, we expect that there will be more collaboration between human and robot. And many researchers believe building the functional part of a robot using a soft material will be much more comfortable than the hard counterpart. Finally, we show a function or the movement of a heart using a silicon rubber. Here, if you want to mimic the same functionality using a rigid plastic or motor, it will be much more complicated. We can say almost impossible. So in that sense, we can say a soft robot can bring a new functionality which we didn't see before using hard material. Apart from that, the operation of the fabrication of this soft robot can be much more simple because you can fabricate most of this soft robot using a 3D printer. Also, these rubbers are low-cost materials, so it would be cheap to fabricate a soft robot. Now, let's look at the main functional part of any animal or robots. Here we shows an elephant trunk. This organ is completely soft organ, which is capable to perform a variety of tasks, ranging from very strong to delicate tasks. Strong tasks include like carrying the tree trunk, and the delicate tasks include like picking a small peanut from the ground. And this structure doesn't have any bone. This is the best example we can show a completely soft biological organ. And if you look at the main functional part of this organ, we have a sensitive outer skin, which composed of a sensor, which is a receptor cells, and conductor that are nerve fibers. The main function of the sensitive skin is to collect stimuli, both internal and external stimuli. The internal stimuli help to understand the position of its trunk and to perform multiple tasks. And external stimuli such as temperature or force help to interact with the outside world. Now it have a bunch of fibers inside the trunk, which is the actuator. The main role of an actuator is to produce motion. Basically, it converts a chemical energy into mechanical force. Then the whole structure, trunk itself is a manipulator, means it can control the movement direction to perform its task. In the last few years, there have been a growing interest in developing soft functional material using artificial material, which can mimic the function of these body parts such as skin, muscles, and manipulator to develop a new class of robots called bio-inspired soft robots. And that is the main inspiration for us to work behind this project. Now let's look at the main objective of this work or thesis work. This thesis described the concept of programmable material with tunable physical property applicable to soft robot. The term programmable means it brings some unusual engineering behavior when you apply an external stimuli, and then using this material, you can develop this functional part of robots. You have three main sub-objectives. The objective one, programmable material for electronics. So here we want to develop a strain sensor and conductor, both from a single material by programming a nanomaterial's electrical property. Now the objective two is a program material for actuator, where we want to develop an actuation system with a tunable pressure inside a soft material. And the method we want to use is liquid gas phase transition of a stored liquid using an efficient electrode. And the third part is a programmable material for manipulator, where we want to develop a simple manipulation technology using a single chamber soft body instead of a multi-chamber. And the method we use on-demand stiffness change. So in objective one, our objective is to program the electrical property. In object two, tune the pressure, physical property pressure inside a soft material for an actuation system. And in third, it's control the stiffness or tune the stiffness to develop a manipulator. Now let's look at each work one by one. Programmable material for stretchable hybrid E-screen for software parts. So before going into detail, let's look first at a difference between a strain sensor and a stretchable conductor. Consider a nanocomposite, a stretchable polymer filled with a nanomaterial having a length and resistance R. If you stretch this nanocomposite, its resistance will change. The change in resistance could be used to predict the change in dimension. That's how a strain sensor behaves. The performance of a strain sensor is usually defined by a gauge factor, which is nothing but the change in signal with respect to the strain. Now, this nanocomposite could behave as a strain sensor if you have a high gauge factor, which obviously comes if you have a large change in resistance. That is a large change in resistance. Now, this nanocomposite behave as a stretchable conductor if you have a low gauge factor, and the obvious condition is to have a small change in resistance. So the people working in strain sensor, their objective is to obtain a large change in resistance. The people working on stretchable conductor, their objective is to somehow get or suppress the change in resistance. Now, fabrication of a strain sensor, I would like to say it's more relatively straightforward. If you take a polymer and if you have a low percolation or low density of nanomaterial, usually it behaves as a strain sensor. But obtaining high conductivity is challenging, usually using nanomaterials. And people use different tricks or methods to obtain this, to suppress this change in resistance to behave as a stretchable conductor. Now let's look at some of the work, how these conductors are made today, or how researchers, what kind of strategy they adopted to make stretchable conductor. Now here a group of researchers are trying to make a stretchable conductor using AG flakes and CNT with a filler concentration of around 80%. So by increasing filler concentration and sometimes using some surfactants to have a better binding, you can increase the conductivity. And here is another group of researchers trying to develop a stretchable conductor by engineering the structure. So having a buckled structure, you will somehow reduce the strain on the non-conducting part. And as a result, you can minimize the change in resistance. Here is another group of people. They were trying to develop a sensor and conductor. And on the sensor, you have a straight line, and the conductor, you have a serpentine-like structure. In that way, you can minimize strain on the conductor part. Or by using a different filler material. Some material have a higher conducting property, and some have a lower conducting property, or by changing the filler concentration. So you can play all this game like of changing either filler concentration, or by engineering the structure, you can have a either large change in resistance or a small change in resistance. So the overall objective here is that to suppress the change in resistance to get a conductor-like behavior. Generally speaking, a sensor with a lower filler concentration should behave as a sensor. And if you use the same filler for the conductor, and general approach is to increase the filler concentration. Now we propose a quite different approach for this. Let's look at what is the approach it is we adopted to get a high conductivity. Consider two nanomaterial, say nanowire, having resistance R1 and having resistance R2. Now we can represent this electrical network as between these 2 points, A and B, as R1 delta R2. So here the delta indicate the contact resistance at the point where these two nanomaterial contact. So when you stretch this nanocomposites, the poor contact resistance cause a slippage. So the contact resistance can go high. And that's how the strain sensor behave. especially at a lower filler concentration. So the people adopt this method. The classical approach is to increase the filler concentration. As you increase the filler concentration, you open new electrical network, and thus you open a new path for the electron flow. But an increasing filler concentration could affect the mechanical property of polymer, and it will be costly because the nanomaterial is very costly. Now we propose a different approach by programming the microstructure or nanostructure of this conducting nano network through welding. By welding, you can eliminate this contact resistance. Also, you can put some constraint for the slippage in most of the nanomaterials. So as a result, we propose we will be able to suppress the gauge factor or control the change in resistance. In that way, the sensor-like behavior could convert into a conductor-like behavior. And we expect both sensor and conductor could be fabricated from a single material. Now, to prove this concept, we first fabricate a polymer sponge, and then we cut into a small strip, and then we added 2 electrodes, one on the left and right side. And in the middle portion, we coated a silver nanowire through a method of deep coating. We analyzed this sponge first in a CT scanner to make sure that pores are well connected and the size of pore is quite matched with that of silver nanowire. So when you deep coat, the silver nanowire will deposit in the pore walls and you get a conducting nano sponge. Now we show the change in resistivity of sample with respect to the coating cycle. As you can see, as you increase the number of coating, the resistivity reduces and sample become more and more conductive. And that's the classical approach, right? So we stop at the third coating here, where you have a barely coated silver nanowire, meaning that the density of silver nanowire in this sample is very low compared to highly conductive sample. So we believe this could be an ideal sample to prove our concept of welding. Now we took this nano composite and then we applied a voltage to this electrode. We apply 4 voltage ranging from 1 to 15 volts for 30 seconds. As you apply the voltage, a small amount of current will flow through this nano composite and the current will heat the junction of nanowire, and as due to the heating, the junction will modify. Here is the result of welding. We show the resistivity with respect to the time of welding at different voltage. As you can see, initially the sample resistivity is very high, around 60 kilo per millimeter. And as you apply 1 voltage, its resistivity reduced drastically and it's quite saturated. Then we increase the voltage to 5, 10, and 15. And the sample became more conductive at the end. And that is saturated, it meaning that there is no meaning you increase voltage further. If you increase the voltage, it may burn your silver nanowire, so we stop after 15 volts. At the end of the welding, the resistive sample became more conductive and the resistivity reduced by 80%. This is all because we believe it modified the junction. So it means you can control the contact resistance by welding. Now this sample is without applying a strain. Now we want to check how the welding could affect the gauge factor of this sample. So here we show a tensile test and change in gauge factor by applying 50% strain on this sample. And we apply this strain cyclically for 30 cycles. Here is the result of this test, change in gauge factor with respect to the welding. The y-axis shows the change in resistivity and the right y-axis shows the strain. Means here the blue curve is strain and the black curve is the change in resistivity. In the pristine condition, you have a large change in resistivity. It means the behavior is more like a sensor. As you apply the 1 volt and then 5 and 10, 15 volt, at the end of the welding, you can see the gauge factor suppressed and it approaches close to the 0. And this is exactly we need for a nanocomposite to behave as a stretchable conductor. So what happened here? If you look at this image of silver nanowire, before welding, the junctions are loosely connected and slippage is possible. And after applying the voltage, the junctions are modified. And of course, you apply constraint for slippage on many of the nanomaterial. And this could control the gauge factor. And at the end of the welding, I would like to say before welding, you had a gauge factor of 2.1. And after welding, you have a 0.29 with close to 0. And gauge factor is reduced. Also resistivity reduced and the sample become more conductive. So we can say The strain sensor-like behavior is now switched to a conductor-like behavior, and that means you can fabricate both strain sensor and conductor using a single material. Now we prove the application of this concept to develop a hybrid E-scan for an action figure. Here we show an action figure with and without applying a skin on the right leg. So first we develop a skin on the right leg. You can see here. Then we develop a two silver nanowire network, one on the left side and one on the right one. We perform a bending test on this leg, meaning that it take two positions, straight and bent. While you bend, the skin here will stretch and the resistance of the network change. As you can see, a large change in resistance on the right skin, right network, meaning that it can behave more like a sensor. And you have similar behavior on the electrical network on the left side. Then we apply a voltage between this network on the left side, meaning that we're trying to weld the silver nanowire, and the behavior changes. Sample become more conductive and the gauge factor also suppressed. So this curve, red curve, behave more like a conductor. The black curve before welding was more like a sensor. So now we have two networks, one on the left side, one on the right one. On the left side, you have a more conductor-like behavior, but on the right side, you have a more sensor-like behavior. So we can say now we have a hybrid skin with sensor on the left side, conductor on the right side. And initially, if you have listened, like on the elephant trunk, you have an E-skin with a sensor and conductor. Sensor are receptor cells and conductor are nerve cells. In future, software boards require these kind of multifunctional electronic skins. So in conclusion, here we programmed a material structure at nanoscale to turn a sensor into conductor through E-welding. By doing so, we drastically reduce the number of particles needed for conductivity. And we believe this kind of direction of programming material of electronic property will be suitable to develop a stretchable conductor and stretchable strain sensor from a single material. Now we go to the second part, the low voltage driven quick tunable pressure in a soft material for compact actuation system in soft robots. So before going into detail, let's look at the classical fluidic actuator. A classical fluidic actuator uses a power source to run a motor or pump, which generate a compressed fluid, and we supply it through a valve tubes to the actuator. Then, depending on the way you design the actuator, it produces a large transformation. But generally, it looks bulky because you have the motor, pump, and valve, this kind of system, and it could cause not good for many of the portable applications. It's an example. We just took it from Google, and where you can see a motor, pump, and valve control system. So our objective was this work that we want to eliminate this motor and pump and operate or develop the pressure inside a soft material to develop a compact actuation system. So in future, we need such compact, low voltage driven compact actuation system without any noise for our soft robotic application. So there are some work I've done in the past. You can see in this first figure, they're trying to get some membrane expansion through a liquid gas phase transition. Here was another study where you get similar membrane expansion using some carbon heater. So it can produce a little bit larger expansion for some of the soft robotic application. Here is an artificial muscle which produces a small deformation, and it takes several minutes to actuate it. So all here, one thing is missing is a large transformation and a fast response. For a fast response, we need a better heating element, maybe a three-dimensional heating element, where this heating element can come with the fluid on over a large area so that you will improve heat transfer coefficient. So to obtain a large transformation, we propose a new design and a new heating element. This structure have a top corrugator enclosure and a 3D heating element, which have a better efficiency. So this kind of actuator can store sufficient amount of fluid to generate any required amount of pressure for the actuation In that way, you can get a large transformation. And we also take some advantage from the structure. Also, we have a better heating element, which is important factor in determining the speed of actuation and also to have a better heat transfer coefficient. Finally, we have a fabric layer to produce a bending motion and the bottom enclosure to for final sealing. So once you have all these components, you can assemble the structure and fill with the fill fluid using a shut-off valve. And here is a final fabricated sample. So the object here to obtain a large amplitude, a fast response, and also to make it portable. So to obtain a better response in the forward actuation, we use this heating element made of microfibers of steel. So it's under the same image, you can see it's highly porous, and the advantage is that you can have a large area of contact with the fluid. In all these applications, one important thing is we need a stretchable or at least flexible heating element. So here this heating element is a flexible and the resistance does not change while you bend it. And we performed the electrical test to make sure that it have a high current carrying capacity. So initially we're trying to fabricate a heating element using silver nanowire and carbon nanotube. And one drawback is that their resistance could change while it deforming, like bending or stretching. And when you supply the high amount of current due to heating, its resistance could change. But this heating element have a stable resistance, even at high current. Finally, we show its ability to convert the electrical energy into heat at the lower input power, and this is a very good heating element. We can generate a temperature of more than 80 within 10 seconds just using 5 watt, showing that it's a very good heating element compared to most of the existing flexible heating elements. Also, this could be a 3D, flexible and porous, and we expect it can perform much better than the other heating elements. So here is the actuation video of our actuator. It uses a working fluid, ethanol, and power equal to 35 watt in a preheated state. It doesn't use any motor or pump. It can produce large transformation in limited time. They are much faster compared to most of the previous studies, I think. And we should keep in mind that this structure is quite big. Work against gravity, it weighs around 40 to 50 grams. So in such a large structure, heavy structure, such a large transformation, we can say at this input power, it produces really faster motion. So this is a real time video. Now let's look quickly at the results like velocity and pressure. We show velocity in pristine condition and preheated state. Of course, in pristine condition, it's could take around more than 40 seconds at the 30 watt in power. Here we should consider that the structure is quite big. It's a large structure, so you need some initial warm-up. But once it's preheated, in the second state onwards, its speed increases dramatically. Because the pressure developed quickly, it uses a pressure around 15 kilopascal. Of course, you can generate more pressure if you want, if you store the sufficient fluid. In a preheated state, the pressure developed faster because of the stored thermal energy in the previous states. So in such a large structure, this amount of pressure in limited time look like it's faster. So here we show the time of forward actuation. In a preheated state, you have getting faster when you increase the input power. At around 45 input power, it took only 7 seconds to produce the large transformation. For such a big structure, 45 watt power could be considered as a smaller, and it uses around 20 to 22 volt and 1 point some ampere current to actuate. Of course, reverse actuation is a little bit slower because we rely on the passive cooling. It requires an active cooling system to speed up the reverse actuation. But even 20 seconds is not very bad actually. And it can generate 1 Newton force. We show the force generated by the actuator at different input power. With the 45 watt input power, it could generate up to 1 Newton force in less than 10 seconds. So generally speaking, it can produce large transformation in limited time, and it can generate the sufficient pressure required for the transformation in limited time. Now let's look at the thermal image of this actuator in the forward actuation and in the reverse actuation. You can see in the forward actuation, the wall chamber come around 78 degrees Celsius and 78 degrees Celsius, which is the boiling point of ethanol. If you want to reduce this wall temperature, one way is to use a liquid with a lower boiling point, for example, a liquid with 56 degrees Celsius. But on the gripper surface, you can see the temperature is around 45 to 50 degrees Celsius. You can reduce the temperature of this gripper surface by increasing the thickness of this the skin on this side. Now for the reverse actuation, you can see at the end of the reverse actuation, if they cool to the initial temperature, it means it have a stored thermal energy which could be used in the next cycle. That's why the speed of actuation is higher in a preheated state. Now we have a simple explanation why we use a corrugated chamber-like structure over the rectangular shape. Here in a corrugated shape, you have a large surface area around 10 times more than the simple rectangular chamber. So all this large area can give a better heat transfer coefficient to the convection heat transfer. It should help you in a reverse actuation. Now, in this wall temperature are deliberately made thinner. This smaller thin wall temperature will have a lower thermal resistance, which will also help in a heat dissipation. So all these large surface area, thin wall chamber should help in a better heat dissipation in a reverse actuation. So in that's why we have a reverse actuation within like in 30 seconds, which is not very bad. Now, finally, we show the application of this our actuation system. We develop a soft gripper. So it can grip your bun of 65 gram in 30 seconds, and it can release it in 9 seconds. This is operated directly using electrical energy. We didn't use any pump or motor, and there is no noise. The system is compact and portable. So in a conclusion, we can say we showed a quick pressure change in soft material for a larger transformation in limited time using an efficient electrode. We developed a portable, easily controllable soft gripper from this actuation system. So that is the end of the second presentation. Now let's go to the third and final part, which is tunable membrane stiffness in a stretchable fiber for programmable shape change in software box. So first we go to an introduction part, which is a pneumatic manipulator. Here is a work done by an MIT group where they develop a soft manipulator. If you look at the soft manipulator, generally they are multi-chamber segmented system. Means each segment will have 2 or more chambers. And of course, if you need a complex motion, then you need a number of segments, and then you will increase the tubes and walls that is needed to control this actuation or the deformation. So generally speaking, it can increase the complexity, and sometimes these soft tubes could increase bending stiffness at some locations. Here is another work where they use a 4-chamber system. So in all these things, chamber, as the number of chamber increases, the number of tubes and walls controlling this could increase also. Now let's look at biology and look at some worm, and they usually use a single chamber system. So in generally, the worms use a circular and longitudinal fiber to control the stiffness of the skin. Here you can see they create a stiffness symmetry that is required for bending through a co-contraction of their muscle fiber. So the worm uses a muscle fiber to control the stiffness of the skin for shape change. Now, inspired by the role of muscle fiber, we want to fabricate a stiffness tunable fiber to control the shape of the soft body. So the main objective of this work is to develop a fiber-like structure with tunable stiffness that could use to control the shape of a soft body. So before going into detail, first we did an Embacca simulation here. You can see a single chamber which expands in all directions, where its stiffness is same everywhere. But as you introduce some stiffness and symmetry, it could produce some complex motions. So here, the fiber is stiffer than the skin, and it prevented the deformation between these 2 points. We used around 30 times stiffer than the skin of the actuator. Here we need a change in stiffness. So we need to fabricate a fiber which can tune the membrane stiffness at least 30 times or more than that, but without increasing any bending stiffness, because this manipulation itself is a bending process. So if you increase the bending stiffness, then it will be a hindrance for the bending. So we need an increase in membrane stiffness, but no increase in bending stiffness. So to obtain a large change in membrane stiffness, we put forward this concept of hybrid fiber using hybrid material. It's simply, if you choose 2 material with stiffness E1 and E2, you can connect them either in a serial connection or in a parallel connection. And the effective stiffness will be given by this equation. You can denote by this equation. Now, if you plot these 2 effective stiffness with respect to the volume fraction of the first material F1, you can get this graph. For a specific choice of E1, which is 1.6 gigapascal, we consider it as highly stiff. But E2 for a range of value starting from 0.6 gigapascal, which is moderately stiff, to 100 kilopascal, which is almost soft material. Now, in a parallel connection, you can see there's a linear relationship between as you can see in this equation. So E total linearly vary with E2 and F2. So meaning that the stiffness will be always high until this F1 approaches very close to 0. But with F2, the picture is a little bit different. The stiffness of this hybrid material could reduce drastically as E2 becomes softer and softer. When E2 equal to 100 kilopascal, as you can see here, there's a large reduction in the stiffness in the hybrid material, even for a small value of F2. Meaning that if you connect a highly stiff material E1 with a very soft material E2, this hybrid material becomes soft and stretchable. So this gives some idea to develop a stiffness tunable hybrid fiber. So how it works? So we show here a picture, highly stiff material, which is a cotton fiber, and a soft material, which is a Ecoflex. By connecting these 2 materials, you get a hybrid fiber. And by making this soft part softer and softer and very soft, then you can easily stretch this hybrid fiber like a stretchable material. So this soft part enable a good stretchability for the hybrid fiber. Now it's interesting, since the volume fraction is small for the soft part, I can, by locking or unlocking the soft part, I can control the stiffness of the NDR fiber, because the stiffness of NDR fiber now depends on the stiffness of the soft part. When it's locked, it becomes highly stiff. When it gets unlocked, it becomes highly soft. So we propose using a locking mechanism using phase change material called gallium, which is a low melting point metal. So we are planning to introduce a locking mechanism inside this soft part using this gallium to lock or unlock the soft part. In that way, I can control the stiffness, membrane stiffness of this hybrid fiber. Now, this is just an example of hybrid fiber. The actual fiber looks different. Before that, we need to design this hybrid fiber, for which we use this graph for designing. So designing means you need to determine the volume fraction of the stiff and soft part. So here the blue curve indicates the semi-log plot of the effective stiffness of the hybrid fiber using Ecoflex and cotton in serial connection. And the red curve indicates that in parallel connection. And here is the hybrid fiber. The blue curve, when they are in connectance here, if you connect this soft fiber with the stiff green part in a parallel connection, you get this curve. And the gray area here indicates the modulus of your soft body that you want to manipulate. Now, we need to fabricate a hybrid fiber with a stiffness quite comparable to that of the soft body manipulator, soft body of the manipulator. And obviously, it is a point where the blue curve meets the gray area, which is at the point A. Now, an equivalent soft part is F2 equal to 10%, but meaning that by choosing the soft part 10% of volume fraction, we can fabricate a hybrid fiber with the stiffness comparable to that of the soft body. Of course, you can increase the volume fraction of the soft part further, for example, 20%. But if you increase too much, say 50%, then the soft part volume fraction will be high. Then we need to introduce a locking mechanism using gallium. Gallium could have some bending stiffness. So as in the beginning we said, we need a change in membrane stiffness and we don't need an increase in bending stiffness. So a larger volume of soft part could lead to an increase in bending stiffness. So we want to minimize the soft part as much as possible, but without compromising the stretchability. So we believe a volume fraction of around 10 to 20% for the soft part should help to design a hybrid fiber with having stretchability quite comparable to that of the softer part. Now for the stiff part of this one, either you can use a completely cotton fiber, that's fine, but or else you can also use a mixture of cotton and Ecoflux itself, but they should connect it in parallel. So here we adopted that method, and the parallel connection curve is given by the red curve. We reinforce Ecoflux with the cotton area of cross section around 50%. So just using by 50%, you can see you can make a highly stiff material or stiff part. So now by locking or unlocking, you should get a approximate difference of around 100 times if you choose F2 equal to 10%. Now, this is the schematic diagram of our hybrid fiber. You can here the green part indicate the stiff part, but here is the soft part, and you can see a locking mechanism inside. Here is the enlarged view of the locking mechanism. You have a gallium structure with a heating element in the middle. The gallium connects the two stiff parts. When you supply current in this heating element, it generates the heat, the gallium melt, and then it will disconnect this two stiff part. And when it solidifies, it will reconnect the stiff part. In that way, you can either lock or unlock the soft part. Here is the hybrid fiber structure. The green actual fiber is the green part here, which is a stiff. Here is the stiffness tunable part. Here F2 equal to 5%, but we fabricate a range of fiber starting from 5% to 20%. With 20%, you get a required stretchability, and we use this fiber for our actual application. Now let's look at the stiffness change and repeatability of the stiffness change. To check the repeatability of stiffness change, we use this force displacement curve in a tensile testing machine. So you place your hybrid fiber in a tensile testing machine and you pull it to around 3 mm, and you record a large force when the gallium is in solid phase. It means the soft part is locked. And at point B, we switch on the power and the gallium solidified. The gallium switches to solid to liquid, and you unlock the soft part, and then the force dropped and reduced drastically, indicating that the stiffness of the fiber changed. Then we reverted this fiber back to its initial position, and the gallium is allowed to cool to regain the stiffness, and the test is repeated. The result shows that the stiffness change is repeatable. Now, in order to quantify the amount of stiffness change, we use the stress strain curve with the soft part locked and unlocked. So the blue curve indicates the soft part is locked, the stress strain curve when the soft part is locked, and the red curve indicates the stress strain curve of the hybrid fiber when the soft part is unlocked. As you can see, there is a difference of around 100 times in between these two extreme states. So we have around a stiffness change, a membrane stiffness change is around 100 times between these two steps. So initially our objective was to obtain at least 30 times in the stiffness change, but this could give a more than 100, and it should be sufficient for manipulation application. Now let's quickly into the time for the stiffness change. Here we It shows the video of a phase change, and using this optical image, you can find out that we can unlock the soft part within 3 to 4 seconds using an input power of 3-4 watt. That's a small input power, and you can quickly unlock the soft part. Stiffness regain takes some time because it's a cooling process. Usually it takes 1 to 2 minutes. But yes, we need to improve that stiffness recovery stage in later studies. So once you have the hybrid fiber, you integrate your hybrid fiber in your soft actuator. We connect the hybrid fiber only at both ends, and the middle part is free to move inside the channel. So we connected this fiber on the top skin and the bottom skin to control the deformation between these 2 points. Now by changing, I didn't show the locking mechanism here, but by locking or unlocking this part, you can create the stiffness asymmetry required for bending. And here we show a bidirectional bending. So we use a single chamber actuator, and we have a set of fiber integrated on left and right side. Then you unlock the fiber on the right side. Here the fiber is locked, and then you can bend it to one direction. Then you revert back this actuator back to its initial position, and then you pull the gallium to regain the stiffness of that fiber on the right side. And it takes some pulling is stiffness regain take 1 to 2 minutes. So I'm just a bit speeding up. So now it's completely cooled and stiffness is recovered. Then you unlock the fiber here, and then it can bend towards the right side. So in that way, you can control the movement direction by controlling the membrane stress. Now, this is a complex shape evolution. Here, they have multiple fiber inside, and you can produce a complex shape change in the soft body. Now, as a conclusion, here we proposed a new concept of hybrid fiber with tunable stiffness to control the shape change of a single chamber soft body. So just through stiffness change, you can replace this multi-chamber system with a single chamber system. Now we conclude the whole thesis work here. This thesis focused on programmable material for the functionality of sensing, actuation, and manipulation in soft robots. First, we showed programming the nanomaterial electronic property using electrical welding to fabricate a sensor and conductor from same material. By doing so, we drastically reduce the filler quantity, and we believe it have a limited effect on the polymer's mechanical property. In the second part, we showed a quick pressure change in a soft body through liquid gas phase change using an efficient electrode to produce large transformation. Using this approach, we developed a portable, easily controllable soft gripper. The third and final part, we showed the shape change of a soft body using a new stiffness tunable hybrid fiber. Using this fiber, we developed a simple robotic manipulation technology using a single chamber soft body instead of a multi-chamber system. If applied together, these 3 concepts could result into cheap, light, and easily controllable new generation software board with augmented functionality. And that is the end of this presentation. Thank you.